my talk is going to be somewhere between a demonstration, tutorial, and maybe experience report about using USRPs and the Octoclocks that Etus sells in the GNU Radio framework to time synchronize the clocks and time synchronize radios that are connected to different computers on the same local network. So why did we want to do that first? I mean, there's a bunch of reasons to do time synchronization, but the reasons we had at first in our team, in our lab, was that we want to make a data set for some machine learning things with a bunch of different transmissions at different frequencies and different times. And we want to be able to label properly what are the time and frequency localizations of all of these signals to do, for instance, signal detection, wideband signal sensing, stuff like that. And to generate that, we didn't want to have all the transmitted signals have a preamble that allows us at the receptor to say, okay, this is the beginning of the transmission, and then a preamble at the end saying, okay, this is the end of the transmission. That wouldn't be very realistic. So the goal was to have an external way outside of the RF field able to correspond the samples stored and recorded at the receivers with the time, the transmission times that the transmitter knows about. And maybe it could be a teaser that eventually we plan to release some kind of data set about stuff like that. So to do that, we didn't really want to invest in new stuff, and we wanted to stick with the hardware we had available, and we still have available, and use the API available with GNU Radio and the UHD drivers. So for this presentation, I'm trying to first tell you about how we did this synchronization, and to show some metrics, some measurements of the timing error we can achieve. And to do that, we're going to try to compare the time we have from this time synchronization system and the timing that a correlation with the preambles tells us. Okay, so first, what is the hardware we have? So we use the CorteXlab room that is actually available to everyone if you want to. And we have, for this purpose, two types of USRPs. One older generation, the 2932, which is based on the N210 family. And also the 2944, which is a specific instance of the X310 USRPs. We have like more than 20 of the first kind and a few, like in this case, 4 of the second kind. And as I said before, all of these USRPs are individually connected to a different computer, and all the computers are in the same local area network via Ethernet. And so all these computers have to collaborate in some way to share and like the triggers and the clock resets with each other. Okay, and so this slide is kind of 2-in-1. The first element that's quite useful is that you can see the most interesting thing is the gray elements. So the light gray are the location of the 2932 USRPs inside of the room, and the dark gray are the 2944. The blue ones are all other types of model that we're not using here. And as you can see, they are linked in some way, and they are all connected to an octoclock, which is a device that transmits both a 10 megahertz sine signal that can be used to synchronize the frequency and the sampling rate of the radios, and also a PPS pulse, so 1 pulse per second. And since these octoclocks, as the name implies, have 8 outward connections, we cannot plug all of the radios into the same octoclock, of course. And so we have a tree system where we've got one octoclock that gives out time synchronization signal to the other 4 ones, and these one give the signals to all the radios. Um, I'm going to point out that it's going to be useful for the results at the end. The USRPs that are 10, number 10, 11, and 30 and 31 are the 2944. We're going to see some difference in the results. Okay, so as I said, what's going to be useful in hardware to do the the time clock synchronization is going to be that PPS pulse. So it's basically a square wave that happens once a second and that lasts, I'm not too sure, either 250 milliseconds or 2.3 seconds, something like that. And we did some measurements to compare the rising edge of this PPS across different octoclocks, and we can see that these are the two extreme cases, especially the one on the right. But we are still around the nanosecond difference between the signal given by two octoclocks. So it's fairly tight for the frequency and the sampling rates we are going to use. Like we are going to use up to 5 megasamples per second, so that would be, yeah, a few hundred times more than what we need. Okay, so this was the hardware setup. Now, what is the software that we can use to do that? Because we didn't want to have to develop new drivers and new APIs to do that. So there's one element. The UHD source and sinks block, they can use tags. So the source block that you can use with the receiver, it outputs both an RX rate and RX time tag that gives you the sample rate that the USRP is actually set to, and that gives you, for that specific sample, what the clock time was at the moment this sample was sampled. And these two tags are emitted both when the stream starts, so when you use that, it's the very first sample that will have that tag, and it's also triggered when there is an loss in continuity, so basically when there is an overflow. At some point you lose some samples, so it sends you this information so you can actually know what the new time is. It is actually, if you do some hacking, possible to trigger the new emission of these tags, but outside of an overflow, but it actually does not update when you update the clock, so it's not really that useful for this. But we'll see that there's a simpler way to do things. And on the other side, on the transmitter side, so you can set a burst mode, so you can give out a chunk of samples that you want to send continuously. This will both tell the UHD driver to not wait for sample after that, so you can actually not send anything for a time before sending a new burst, without it being complaining and putting out underflows or anything. It actually shuts off the radio side, like the amplifier, so you can actually avoid having interferences from that radio card. And so you can either have a tag at the first sample of your burst saying how many samples this burst is long, or you can have one sample at the start and one at the end. So in this case, you would call them SOB for start of burst and one for EU, end of burst. And you can accompany this first tag at the beginning of the burst with a TX time that contains the time that you want these packets to start transmitting. So you can say, okay, transmit that in 2 seconds if you want. And it's going to transmit that regarding the clock that's inside of the USRP. So the goal here is to synchronize the clocks of all the USRPs on the same time, and so that when the transmitter says transmit that at t plus 2 seconds, the receiver can know that, okay, it was transmitted at t plus 2 seconds, and it hopefully can relate that t plus 2 seconds with a specific sample at the reception. So this is for the tags. There's also some API that the UHD blocks have. it's not available on the messages, I believe, that you can input inside of the blocks, but you can still call these methods of the UHD blocks either within the flow graph or, as you will see a bit later, via other blocks if you give them the right information. So one element very simple is that you can ask the UHD block to give you what the USRP time is at the specific time. You can also ask it what was the time when it received the last PPS, so the last pulse. It can be used to know how long happened between now and the last PPS. So you can know if you can expect the next PPS in like 0.5 millisecond or just right now or anything. And you can also tell it to set the clock to a specific value when it receives the next pulse. And this is what we are going to use. So all these elements, they handle not a float second, they use a specific time spec object, which basically you can use as a integer number of seconds and a float number of seconds. But there's a few elements that you can convert from this semantics into like float seconds, like you can manipulate in Python or C++ or a bit more easily. Just a quick note that an element that we found out when we started using that. So we started developing this with GNU 3.9, and it appears that the UHD that is bundled with makes it so that the X310, so the 2944 USRPs, they don't use the rising edge, but the falling edge of the PPS to trigger. So we had a constant 0.3 second delay between what we expected and what we actually had. So if you want to do something like that, use GNU 3.10. It's going to avoid you some trouble. Okay, and another thing that we are going to use at the end is you can also trigger the beginning and the start and the end of a streaming. So you can tell the UHD driver and USRP block to, okay, now commands start giving us new samples or stop giving samples. And for instance, when you say that, when you trigger the start stream this way, the first sample will have this Eric's time tag. Okay, and the last element we are going to use is the snippets, a very handy GRC element that allows you to add block snippets of code at specific times in the run of the Python code that GRC generates. So either at the start or just after the initialization of the blocks or at the end. And for instance, one very useful thing it can be used for is you can give out objects that the top block knows about to blocks that you coded. And for instance, if we have a block called scheduler that we are going to use later, that we defined to have a function that received an object, and we can give it the UHD block object. And so it means that the block will then be able to call all the function, all the method and attributes that this block has as if it was the top block. So you can use all the available API as you want. It's very, very useful. Okay, so now for the implementation side. So we have, of course, a transmitter and a receiver. The transmitter is fairly simple. We first have a source. So in this case, we generate two Z of shoe sequences that have a 0, in theory, autocorrelation with itself. So this is going to be our preamble. And we are actually going to send two of those back to back as a big preamble. Then we have a block that basically triggers the sending of these two elements, this preamble, when it's time to do so. And that gives that to the USRP sync set to whatever frequency sample rate we want. And at the bottom of that, we have a custom, like the two blocks in the middle are custom Python blocks. Eventually, I kind of want to transfer the TX sync to C++ so it can run a bit faster, but it works fine for now. And so, yeah, we've got a scheduler at the bottom, which is going to, as we'll see later, handle the reset of the clocks, communication with the other nodes, and stuff like that. And this communication is done via ZMQ message blocks that we'll see a tiny bit later. So these are like standard blocks. And on the receiving side, so we have a similar setup. We also have this scheduler. It's actually the exact same block. We have a receiver that receives the raw signal, and the same ZMQ communication system with the other nodes, the other computers. And at the bottom, we have a fairly simple chain that computes the autocorrelation of the signal at a specific delay. So we know the length of the preamble, we know it repeats, and so we can like basically compare the first half with the second half, and when it peaks, we know that we found the beginning of a preamble. And we use that to trigger a peak, and we use this burst tagger, which is a basic block, to put a tag in the first in the row stream, saying this is where the peak was at, and the RxSync job is to put a tag when the expected receive time is supposed to be, and the last block is a block that's going to compare the location of these two tags to tell us, okay, this was the offset between the two timing methods. Okay, just a quick note. We have like 40 nodes, so we can make a big bus with many blocks, and it actually works just fine. It doesn't complain, just fine. That way, we can have all the nodes sharing all the messages fairly simply, just by having one of those big blocks in every node. Yeah, just as an example, here is like in red and blue, it's the complex preamble. It's the AZF2 sequence, and you can see that it's repeated. There's two elements of that. And when we do the autocorrelation of that with the right length of the preamble, we get a nice peak in the black line. We get a nice peak at the end of the signal we sent. And it also triggers like in this case, it's named CorMax, a tag at this location. Okay, so now a bit of time scheduling, because you need to somehow synchronize all the computers and to have them exchange messages to saying, okay, so first, all the nodes send a message on the general bus saying, okay, I'm node X and I'm running, I'm alive. One of all the participating nodes or computers is in like init mode. It's like the master, the orchestrator. And so it's going to wait for all the nodes it knows it is supposed to participate to say that they are alive. So, okay, they're all awake. We can start the next element. So the next element is to tell all the computers to start the synchronization process. But since this is a communication, it's over internet, it's fast, but still it takes some time. We want to avoid some packets to be received just before a PPS pulse and some packets being received just after that, which would mean that some clocks would be 1 second earlier than the other ones, which wouldn't be great. So we wait for, we listen to the UHD, like time since last PPS and time now, to ensure that we still have at least 1/2 a second left before the next PPS to be sure that we have some time for the packets to arrive and for all the nodes to receive them and start the synchronization process within the same PPS window. And so the nodes, when they receive that message, they start the process. I'm going to describe that a bit later. And when it's done, they send a message back to the init saying, okay, it's done, we're ready. So the initiating node listens to that. When everyone is synchronized, it can start the experiment itself. And so it's going to basically schedule, okay, node 1, send your burst right now in half a second. And then half a second later, it's going to be, okay, node 2, send your burst now, and et cetera, to ensure that there's no interference between the node. So it's going to transmit this order with the number of the node, the identifier of the node that is supposed to transmit, and the moments it's supposed to transmit. So then the transmitter will transmit those and send back a message that is going to be captured by the receiver with basically the same information saying, okay, I'm node X and I'm going to transmit my burst at a specific time, which means that the receiver can check that and place the tag at the expected time it's supposed to receive the burst at. Now a bit more detail on how we do the synchronization. There's a few lines of code, but it's actually fairly simple. So the one element we need is the object of the USRP block. It could be a sync or source block. It works the same. So we get what is the current time. We tell it to reset the clock at a specific value. In this case, it's 0 at the next PPS. And then we have a loop that checks the time that the clock says and over and over again. And so we can see when the time jumps back from basically what it was before to 0, or 0 plus a tiny amount. And so when we see that happening, we know, okay, the clock was reset, the process functioned, and we can continue. And then we can, at the end, send a message back saying, okay, the synchronization worked. Yeah, there's one additional element we need, being that we need to have the receiving stream start only when the synchronization happened. And which means that at first we need to have the blocks not actually send the samples. And one way to do that, using just the GRC parameters that we have, is to have at first the clock synchronized to the PC time, which is like many hundreds of thousands of seconds, and ask the USRP to start streaming at a second one, which is in the past, so it never does it. So it means that you can ensure that it's not going to start streaming until like a few years in the future, so you're good to go. And which means you can then later use these functions, like the first one, to say, okay, now start now at t plus 1 second, and it then will work. Okay. Yeah, and the receiving block, its job is as fairly simple. So it's going to monitor for the RX time. So it will know what so it will store the offset, so the number of the sample that corresponds to this RX time tag. It will also store the time that it's associated with, plus the rate. And so then later it can just count number of samples divided by sampling rate, and it gives you the time. Yeah, and finally the delay block, it's going to look at those two tags that have a different name, of course. And you have to give it the length of this burst, because the expected time from the messaging corresponds to the first sample that is transmitted, and the correlation time corresponds to the last sample. So you have to offset that by how many samples the burst is long. and then it will simply like record, okay, a new line in a CSV file with the ID of the transmitter, the number of samples the offset was, and the translation of that in seconds. Okay, so now it's oh no, yeah, slight additional element. I made it so that these flow graphs can take a bunch of parameters like the center frequency, the sample rate, what are the nodes that that are taking part of in this specific experiment, etc., so that we can actually write some scripts to generate a bunch of different experiments with slightly different parameters to sweep a range of parameters, basically. Okay, so now it's time for some results. So I'm just gonna go back slightly to the, oops. Yeah. So the point was to try to have different variation of transmission and reception pairs without having to exhaustively make each one of them. And so the point was to have like 3 main experiments. In each of them, half of the node are transmitter, half as receivers, and to cut the room in different orientations to have different distinctions, and hopefully like separate the different octoclocks and separate nodes in between the octoclocks they are connected to, etc., etc. We'll see later that it doesn't actually change that much, but I wanted to ensure that it did not. Yeah, and I tried to sweep a few sample rates to see how the delay changes with, like in this case, two center frequencies and around 50 bursts per transmitter, so we can make some statistical measurements of the delays. And what we are going to look for next, we're going to see a bunch of box plots. One element which is interesting is like the average delay, or in this case the median delay, and how spread out it is compared to the median. Keeping in mind that there can still be some delay attributable to some noise in the correlation itself. So we don't expect to have a very precise median. Okay, so I don't know if you can see that. So we've got 2 box plots. So in this case, we are the minimum sample rate that the USRPs can provide. So 200 kilo samples per second. And we've got, like if we look at the one on the left, for instance, we've got 2 types, so 2 colors of box plots. In this case, there's just one line, but it means that the median and the quartiles are actually the same value, which means that it's actually not spread out at all. The blue, the dots are the outlier values, like the really, really extreme values that are outside of the quartiles. And one element is like to help you read this figure. So we have what's the average delay for each transmitter number, so the 3, 4, etc. when it has been received by a specific type of USRP, because it has quite a big of a difference. So for instance, like the first one, the 3 is actually a USRP, it's a type 2932. So when, yeah, here we go. What? What's going on? Yes. So when this type is received by the same USRP type as itself, we get basically always a 12-second offset between 12 samples offset between what we expected and what the correlation told us. And actually fairly, more than fairly, it's really, really stable among all the devices. As I said, these 2 and these 2 are the other types, so which is why there's a difference. And if we look at the other graph, it's the other way around. Is the delay per receiver when the transmitter was a specific type. It's kind of looking at the thing in the other way. But yeah, we can see that it's a fairly stable offset of the same amount of samples with a very, very slight spread, which I attribute to the simple noise of the correlation. And we see that when transmitting across different types, the delay is not the same. I'm not exactly sure why. I would guess that it's probably because the USRPs don't work at the same sample rates inside of it, so there might be some differences in the way the samples are handled. So yeah, when we change the sample rate, we can see that the spread can change a bit. So here I increase to 500 or to 1 megasamples. The interesting element is that for the same 2932 type, it's always 12 samples. It's not actually time-based, this delay. It's really based on how many samples were processed. I'm not sure why exactly 12. That would be a nice question to ask. And the other type also has a fairly stable amount of samples in offset, except when crossing the two types. Yeah, what can I say more? So it works that way up until around 2 megasamples per second. When we increase again the sample rate, we can get a bit higher delays. But yeah, it kind of works the same. And when we change the frequency, the center frequency, it's exactly the same graph that we saw at the previous center frequency. It really depends on the sample rate and not the center frequency, which is kind of what we expected. So I'm going to pass by this one fairly quickly. And so, yeah, to conclude, what I made was just like 3 Python OOT blocks. So just using what the API was without developing new elements of the drivers, and it does work, which is good, which means that it's actually fairly easy to reuse for our purposes and for what you want also if you're interested. And in terms of performance, yeah, just as I said, it's really a sample base, which is good because it means that we can fairly easily compensate for that. We know, okay, it's 12 samples of delay, so we know, okay, just add 12 samples and we're good to go. For this 2932 type, there is a bit more spread for the 2944, but it's still fairly stable. Oh yeah, something I did not mention, what those two 12 samples corresponds to. So for instance, at 200 kilosamples per second, this corresponds to about 50 microseconds of delay. But if we increase the sample rate, we can go down to like 10 microseconds. And I'm sure if we could go up to 10 megasamples, it could go even lower. Yeah. There's a few elements that I would like to. Oh, I made a typo there. I would like to check what happens when it's not the same sample rate between the transmission and reception chains, just to see what happens. And also, yeah, I maxed with the computers that we have in the room. I maxed out at 5 megasamples per second in the reception chain for the 2932 USRPs. So maybe if I switch to C++ blocks, I can see what happens at like 10 megasamples per second, or maybe a bit higher. And yeah, I guess this could also be used like the other way around. Now that we know that this synchronization system works inside of the room, we could use that to evaluate the performance of like preamble synchronization schemes. Like what happens when the noise drops down, or what happens when the length of the preamble reduces, or stuff like that. And so all the code, as much as there is available on GitLab, and there's also a Docker image that allows you to run that directly. Still need to add some documentation, but we want to have it as a tutorial, as a demo on the CorteXlab wiki, so you can use that to either just use that directly or train yourself to use the CorteXlab room if you want. And that is going to be it for my presentation.
What happens is you have the ADC, and then there's some basically signal shaping, or data shaping, so that you can process it further on. Then there's the radio control block in your USRP, and that handles, has this internal timer that reacts to in the end to the timestamps. After that, there is some filtering. There's a CSC filter and 2 half-band filters, I think, in both just one in the N2 series, right?
Sure, but it's irrelevant.
Yeah. No, it's actually not irrelevant, because that also introduces a group delay, like the classical, as you know from signal theory, group delay of a filter. But that's kind of fixed, because it's always at the same rate.
It's after the timestamp.
Exactly. It's irrelevant for the timestamp. It adds a static delay, as long as you use the filters. So what you observe is the delay of processing between the ADC and the radio block. And that is going to be relatively, that 12 samples sounds familiar. Yeah, so that sounds pretty solid. I was a bit surprised about your time setting thing. That was an interesting, I always call it the USRP time setting dance, because it's a kind of a choreography where you have to do this thing where you check whether the time is updated. I'm usually doing something similar, where I just check whether the clock last PPS has changed, because I know I get a PPS every second. So I can I set the time once to some value, doesn't really matter, and then I just observe whether it changed. Then I know, okay, I've just queried just after the last PPS occurred, and I have nearly a second to do this whole thing. And I think you're doing an endless loop where you just set did I get that right? How do you?
In there?
Yeah, exactly. I didn't fully.
So I check what the current time is.
Yeah.
I ask the USRP to reset to 0.
Yeah.
And then after that, I continuously look at the time
Nice.
to see if it went back from what it was before.
Doesn't that run into problem when the USRP has just started and it might just be at 0?
That's why I put it so that it's not at 0 at the beginning.
I see.
That's also interesting, because I thought streaming would start when if my current time is larger than the time I set, but it's actually triggering on the exact time. That's interesting.
Yeah, I guess it checks when the times becomes that value, and then it starts, but it's already that value. It says, okay, it's in the past, and it doesn't do anything. Oh, one thing I didn't mention is that, I'm sure you noticed, the nodes are not exactly the same place, so there is some time propagation delay. But for these sample rates, I computed the time of the radio wave propagation, and we would need to be above 15 megasamples per second to be able to see that propagation delay if the wave was going all the way across the room.